Is my screen visible to you?
Yes,
Okay. So in today it is the seventh live session for basic environmental engineering, pollution and abatement. And let's start with the brief of lecture 31. So previously we had discussed some of the strategies for preliminary and primary treatment of wastewater, and now uh, also various strategies including the secondary treatment. So here we will go into a few design aspects of these secondary treatment processes. So one of the most common secondary treatment process is activated sludge process, which is the conventional one. So here what happens is if this is the influent of wastewater, which will have some amount of BOD, and it goes to the aeration tank where we provide the microbes. They grow by the digestion of the organic compounds or any other compounds that can be oxidized. And here, activated sludge process occurs under the constant supply of oxygen. Now, there will be a lot of sludge produced during this, and that is because of the growth of microbes. Like initially, microbes will grow, and at the same time, microbes die also. So, simultaneous microbes growth and decay occurs. So, the dead microbes they will not be able to do further. So, we need to constantly remove some amount of sludge, like this will contribute to sludge. So, we need to continuously remove that, which is removed in secondary, like we provide settling so that it can be removed. So, some amount is removed. Water can be like effluent can be taken out, which has lower amount of BOD, and some amount of sludge or the mother liquor. It is recycled so that all not all live microbes they are just wasted. Okay, so there are some of the parameters that needs to be taken care of while designing or while uh, selecting or fixing the parameters. So few of the parameters will be known to you, like what is the inlet concentration here of BOD, at what flow rate is it goes in. So you need to decide what volume of tank you should have, what is the time. So what you need, volume of tank. So these are some of the parameters you need to design. Then you need to have a final target concentration. So that might be given to you. So depending on that, you will check what microbe concentration you will supply or amount of microbes needed. Then you will decide the contact time, because you will not provide much contact time. It should be economical also. So considering all the aspects, you do the design. So you include economics also while designing uh, the process. And also you need to check sorry, what should be the recycle ratio such that the processes and what should be the recycle ratio and how much can be wasted so that the process is economical. So here, if we see, then F to M ratio is nothing but what amount of microbes are present per amount of the BOD that needs to be digested. Now, other than that, important parameters are MLSS and MLVSS, which are corresponding to the microbes that are present in um, the aeration tank. Now for that, what is the amount of sludge that is settleable or present in the aeration tank that can be settled? There is a parameter which is sludge volume index, and this parameter can be calculated by allowing the wastewater containing sludge to settle for 30 minutes. Okay, and based on that, you can calculate the sludge volume index. Like out of 1 liter or few amount of wastewater containing sludge, what is the percentage of sludge present in it? So here 30 minutes you are taking because like you have standardized the process. Now to do the mass balance or to find out various parameters, what you do, you can do mass balance. Now mass balance can, I will not discuss in detail or derive mass balance here right now, but mostly mass balance will be input minus output plus generation minus consumption equals to accumulation. Okay, so here there will be two types of mass balance, and first is for microbes and second is for BOD, or you can say substrate. So here microbes are generated. So the terms which will remain is input minus output plus generation. There will be no consumption in case of yeah, consumption will also be there because some amount of microbes will die. So consumption will also be there. Okay, and accumulation is the what remains inside. And another is for BOD. Here BOD is not generated, so generation term will cancel out. Input, output, and consumption will remain. So you do the mass balance for these two to get the values of the required parameters. Now, some of the important parameters, as I mentioned, is hydraulic retention time, which is nothing but what is the ratio of volume per unit flow rate. Okay, so it is the amount of time water spends inside the reactor or in the process. And then cell retention time. So cell retention time is nothing but it is the amount of time all the microbes they or the average time which microbes spend inside the system. And the biokinetic parameters. So biokinetic parameters, they are nothing but the parameters that are obtained from lab scale experiments that include what is the growth rate of microbe, then decay rate, like rate is nothing but rate constant, sorry, growth rate constant, decay rate constant. Then there can be for unit conversion of BOD to CO2, what is the amount of microbes needed or yield factor Y. So such parameters are needed which can be derived from lab scale experiments. So this is how by providing this data you can calculate various hydraulic retention time or some microbe retention time from by doing mass balance. Okay. Now there can be various types of activated sludge process which can be conventional, there can be high rate, or there can be extended aeration. And for supply of oxygen, you can have conventional, tapered, step, and complete mix. Where in conventional one, you just have normal uniform supply of oxygen or constant supply of oxygen throughout the length of reactor, while the requirement of oxygen reduces with the length of reactor. This is because Here it will be more, and it if the BOD goes on reducing, then the oxygen will decrease as its requirement. So for that, what we do, tapered aeration is, instead of constant supply of oxygen, we if this is the oxygen requirement, we have this type of oxygen supply. Another is step aeration. So here the efficiency or the amount of oxygen required is less and the efficiency also reduces. Step aeration is nothing but you provide step inputs of wastewater to this aeration tank, and you provide a constant oxygen supply. So in this case, once the oxygen concentration starts requirement starts reducing, again you provide more BOD so that it balances out. And complete mixing is nothing but you provide uniform distribution throughout. Like here, it will be the input. So this is how constant oxygen requirement will also be there, and supply will also be there. Now moving to the next lecture, another type of conventional treatment is trickling filters. So trickling filter can be both, sorry, it can be aerobic and anaerobic. So far, the activated sludge process was maintained aerobic in condition, while trickling filter can be aerobic or it can be anaerobic. So, this is the image for trickling filter. So, here if you supply air, then it will be aerobic, and if you stop the supply of air, then it turns anaerobic. So it can be high rate or low rate filters where the amount of time which is provided or the retention time provided inside the filter, it can be low in case of low rate or it can be high in case of high rate. So as the name suggests, low rate means more time is provided, like the rate of flow is less. So here you get more efficiency for removal, and for high rate, obviously you will get lower efficiency for removal because the amount of time it spends inside the reactor is less. And super rate filter, the efficiency is lesser, but you can uh, handle higher BOD loading or higher wastewater to be treated. Then you can obviously go for high rate filters. Now here what filters have, they have some packing material. So these are the packing materials, and on this you provide some seeds of microbes, and once like influent goes here, sorry, influent is sprayed through the nozzle and air moves in the counter current direction. So as the water comes in contact with air and microbe, there will be digestion or degradation of the BOD which is present in water. So here the microbes grow, and as the microbes they die, they will be uh, falling down, and it can be collected as sludge. So this water it comes here in the settler where sludge is separated, and again some amount of water is recycled. Now here the mass balance was difficult to be done because the growth of microbes over this filter media, it was difficult to be done. So that is why one correlation which is like general correlation you can use, but mass balance has not been done. The type of filter media you can use is rocks, sands, or some packing material which can be of plastic. So you can have some systematic or random packing inside the filter. Now another is anaerobic sludge blanket reactor. So this is the anaerobic sludge blanket reactor where this is the influent going, and this is the sludge where it is maintained. Now, anaerobic means you are maintaining a closed system and you are collecting whatever the gas that is obtained. So there will be a separator here and you collect the gas from the liquid and liquid can be collected here. So since there is no oxygen supply, anaerobic occurs process and the gas it further can be used for biogas plants. So do you have any doubts so far?
No, it is quite clear.
Okay. Yeah, so here the sludge age, which is nothing but uh, what is the amount of total sludge or mass of the um, microbe inside the aeration basin per unit what you supply, and what is the amount of time this microbe spends inside the aeration tank. It is nothing but it present what is the amount present per unit outlet. Outlet can occur in the form of there can be wastage like you draw some amount of sludge and there will be some amount in the effluent. So based on that you calculate the mean cell age. Now next is the lagoon system. Now lagoon system is nothing but I had already mentioned it occurs under atmospheric conditions, right? So under atmospheric condition, you do not provide any external oxygen supply or you do not provide any external mixing. So what happens is due to diffusion inside the tank or the interaction between atmosphere and the water. So lagoons are nothing but shallow tanks because if you keep more depth, then the interaction of atmosphere and the water will be less for oxygen supply because here the oxygen supply is from atmosphere. So now what happens here is uh, there is one inlet. Now you can say that the layer of water which is in immediate contact will have highest amount of oxygen. Okay, so as you go down and down, there will be some diffusion, but a layer comes inside the tank where the amount of oxygen which is present, it is not there. Like gradually O2 concentration decreases down the lagoon tank, and there will be some region where anaerobic digestion or degradation of BOD also occurs. So this you can say it is a combination of aerobic and anaerobic condition, and the mass balance is shown to you in the lecture where you do separately for this and this, or you can combine also. Now moving forward, uh, next is the sequential batch reactor. So here in the starting of lectures, professor has discussed few um, disadvantages of activated sludge process. Like this sequential batch reactor is nothing but a modification of activated sludge process. So now onwards, we do some modification to have advanced treatment methods of those conventional ones which are discussed so far. So can anyone tell me what are the drawbacks of activated or conventional activated sludge process? Okay, so if not, let me tell you. So in conventional process, what we do is we do use multiple unit operations in series and have a continuous operation, which requires more space. Okay. So now in this case, what we do, so this operates with space or in space. Now here in sequential batch reactor, what we do, we operate in time domain or which time, like we do different batch process in a single reactor. So where we do not have much space, in that case, such type of sequential batch reactor, it it is very useful. So here what we do, once we fill the tank, so during that we do not provide any mixing here. So we statically fill. So there will be some filling time of this. Now after it is filled, we provide some microbes or externally whatever is required. So mix it, and aeration is provided by supply of oxygen. After that, so once it is done, so you fill this. Once it is done, what you do, you allow this reaction to occur to interact microbes with the BOD. So this is react where microbes degrade BOD. Okay. So next is after reaction occurs, there will be a formation of sludge. So here you provide constant mixing and aeration. Okay. After that, what you do, sludge is formed during the reaction. So for that, you provide, uh, sorry, settling inside a settler for microbes or the sludge to settle down. So this is nothing but a settler. So here you can provide mild mixing or no mixing, and aeration is not required here. Now once this settle down, you can decant this. You can separate the sludge, and whatever is remaining, the mother liquor, it can still have a certain amount of solids. So for that you do decantation. So decantation works on the principle of density difference, where higher density uh, material comes at the bottom, and low density will be formed. Layer of low density material will be obtained upwards. So here water layer will be obtained, and you can take this out, and again you keep. So there will be some time gap provided, after which again you repeat the cycle. So average life time taken or processing time here is almost 4 to 10 hours, I guess. And after this, you again repeat the cycle. So all these are nothing but these steps, and these are the parameters which are associated with the sequential batch reactor. So what happens is the cycle time is nothing but the total time which is taken for all the process will react, settle, decant, and idle. So total cycle time is summation of all this TF plus TR plus TS plus TD plus TI. Okay. So this is the total cycle time. Then volume exchange rate, it is nothing but how much you are able to separate after decantation, and what is the amount you fed. Retention time is nothing but volume of tank per unit flow rate of flow rate that is handled per day. So flow rate in meter cube per day. Uh, then solid retention time is similar, like what time solid or microbes spend inside. And also, along with the BOD degradation, there can be nitrification and denitrification occurring. And this nitrification and denitrification is nothing but in the presence of oxygen, the nitrogen it gets converted into, or the ammonical nitrogen, you can say, it gets converted into its nitrites or nitrates. Okay, so this is nothing but nitrification. And if there is limited supply of oxygen for this nitrogen, then this nitrites or nitrates they degrade into further N2. So this is denitrification. So this is all about sequential batch reactor. Now moving forward, granular activated sludge process. Again, it is the modification of activated sludge process. Now, activated sludge process, it handled flocks of microbes, while in granular activated sludge process, what you do, you allow the microbes to grow into granules. So here, I will change the slide. So granular activated sludge process. Here, what you do, the microbes used are some different types. So initially they are very much separated. So when they grow, they come together to form a bigger flock. Now after that, what happens is they secrete some extracellular fluid, and that fluid it is able to keep the microbes intact, and it grows into denser mass. Okay, so it grows bigger over the period of time, and a granule of microbe is formed. So here you can say all the process occurs within a single micro granule. So first layer there will be aerobic layer where degradation of organic matter occurs, and there will be nitrification if there is some amount of nitrogen. So ammonical nitrogen will be converted to some nitrates and nitrites, and they can be eliminated from water. And there will be a layer inside it where there will be limited supply of oxygen, and that layer will have denitrification and further nitrification. So denitrification, where the oxygen that is provided is by degradation of nitrates and nitrites. So nitrates or nitrites they degrade, or they undergo denitrification to release oxygen also, which is responsible for biological oxidation of organic matter. And there will be some layer where anaerobic digestion occurs or degradation occurs of the uh, organic matter. So there will be layers at which the digestion or degradation occurs. Now, since so you can say merits of granular activated sludge process, since the granules are bigger size granules, they are faster to settle. Okay, so it has very fast settling, so you do not need to provide any extra settling or such sort of thing. So there is one process or technology which is well established, which is Nereda technology, where you can say You provide the mixing of these granules. If there is water, you provide mixing of these granules to allow it to grow. And after that, once you allow it to react, if you allow the settling here, then there will be immediate settling of these particles because they are very dense and have more mass, which results into faster settling. Now, another is membrane bioreactor. So, membrane bioreactor is nothing but MBR, or you can say, firstly, uh, here in this tank, there will be two sections. Here you provide aeration where digestion of or degradation of the organic matter occurs. And after that, you do not provide any settling of microbes. So, this further wastewater after degradation of organics, it goes to membrane filtration. Okay, so membrane filtration will separate the microbes or the sludge from the water or the treated water. So here for separation you use membranes. And the membrane unit you can have one unit like one tank for aeration and you externally provide there will be two series of it or you can have one system where you can have sections and you can do the process in one unit. Now moving forward, another type of advanced treatment technology is nothing but phytoremediation and phycoremediation. So here what you do, it is kind of very environment friendly method. So here in phytoremediation, phyto means nothing but related to plants or trees. Okay, so here you utilize plants and tree for the remediation or removal of um, this pollutants from soil or from groundwater or any source. Okay, so here if it is the source of water and there is a tree here or the plant here which is able to take up the or take up the pollutant, then in that case we can use that plant. So here what you can do, use the plant for removal. Later you can recover the pollutant and harvest this this or you can do any utilization of plant. So here there can be different phenomena occurring. So first this phytostabilization. So if you say this pollutants they due to diffusion or any such phenomena due to concentration gradient or bulk motion also of water, these pollutants tend to move from one place to other, which will have the spread of pollution from one place or which is the origin of pollution to another place which was not earlier polluted. So there can be spread of pollution, but by providing such type of plants, you can like there will be some interaction due to which the mobility of these pollutants they it is restricted or it reduces, which is why further it will not get or further any unpolluted place will not get this pollutants. So this is phytostabilization. Then there can be phytostimulation where you take up um, the so here roots of the plant they take up the pollutant and it goes upwards and further transported to stem and leaves or so where they are stored. Then other another is phytodegradation or um, phytodegradation or transformation where the plants they are also able to after the uptake they are able to degrade or change the pollutant into another form which are less hazardous. Also, or this is nothing but transformation. Okay, so what is left is extraction, where it is nothing but stored inside. Now, moving forward, so this plant, as I said earlier, you can remove the pollutant from it. You can recover the pollutant later, and after that, the plant can be removed or it can be utilized further in some form of harvesting, or it can be destroyed. So there are particular type of plant which are suitable for the removal of specific pollutants, and the list of such plants is shown to you in the lectures. Now another is phycoremediation, where algae is used for the reduction or transformation of pollutant. So here you can see in the schematic. So algae, if it is present in the presence of sunlight, what it does, algae, it takes up carbon dioxide and it releases oxygen. Okay, and it can algae can further take up uh, pollutant by adsorption on its surface. It can take up into its cell through cell membrane by diffusion, or there can be some sort of immobilization. Okay, so that by that means algae works. Now, this oxygen which is produced, there will be some natural bacteria which are there inside the water which is treated. So that bacteria, it takes up this oxygen and it further degrades the pollutant which is present inside the wastewater. Now that degradation further releases CO2, and again algae can consume that. So you can say that algae and bacteria, they are working in a synergistic manner to degrade and to remove pollutant from wastewater. So here they can have a horizontal, vertical, plate type or plastic bag type system, or uh, units, where horizontal is nothing but you can have horizontal tubes which is exposed to sunlight, and algae and bacteria are present, and there will be some inlet of wastewater. There can be vertical tubes also. So all these have their own pros and cons. There can be flat plates between which there will be flow of water, and algae will be grown here, and there will be removal. But this plate type is very least used because it is difficult to maintain the water flow. So now moving forward to the assignment. First question is sludge volume index, which is normally calculated as dash. Yeah, so sludge volume index is nothing but what amount sludge volume after it is allowed to settle for 30 minutes per unit MLSS concentration, right? So it is option B. Next question is determine the depth of low rate trickling filter that has diameter of 43 meters. Hydraulic rate is 0.13 meter cube per second. Influent and effluent BOD are given. It operates at 27 degrees Celsius. Uh, Empirical constants Mn and R1. K at 25 degrees Celsius is zero point 0.1 meter per day. The packing media are rocks which have porosity 0.6 and sphericity 0.9 with geometric mean size 80 mm. Theta is given to you as 1.08. So Can you tell me which formulas to be used? Anyone? If not, for trickling filters, these are the correlations used, which are mentioned in the lecture. So here, S is nothing but substrate or BOD concentration in the effluent and in the influent. And this are nothing but K is rate constant, L is the diameter, depth, AS is the surface area, and A is the area of, AS is the spherical particle area, and A is the area of tank, okay? Q is the flow rate. So now if we want to calculate the depth or L, what we need? We need SC, we need SI, we need K, AS, A and Q. Now from the data we can say that we are given the diameter of the tank. So diameter D is given to you as 43 meters. Then loading rate, hydraulic loading rate Q, which is flow rate, is given to you as 0.13 meter cube per second. Now BOD in is given to you as 255 milligram per liter. BOD out is given to you. So this is nothing but SI and SE is 20 milligram per liter. Then temperature of operation is 27 degrees Celsius. Now, why is this temperature required? Because as the temperature varies, the activity of microbes it varies, and you can relate the activity or rate at which microbes are able to degrade the BOD by this correlation. Okay, so here you know what at 25 or standard conditions, what is its activity, and there will be one factor by which you can convert it at different temperatures. Now here the packing media is rock, which has porosity zero point 0.6 and sphericity zero point 0.9. So here the area which is covered by rocks, since porosity is zero point 0.6, you can say that 40% only of the volume is covered with rocks. So the effective area which will be on in the contact will be only 40% out of the rocks packed. And the area for surface area calculation, if you have same material and it has different shape, then the surface area will be different, right? Now here to have uniformity, what you do? You calculate or you have the sphericity of particles, which is a relation of if you have one sphere shaped or one irregular shaped same material, then how much it tends to sphere, so that you can calculate the surface area without because for irregular shaped or such shaped particle, it is difficult to calculate the area. So firstly we will calculate AS, which is given by 1 minus epsilon by psi d bar. Yeah, d bar is given to you as 80 mm. So calculate this AS first, put up the values and calculate it. So 6 into 1 minus zero point 0.6, right, by zero point 0.9 into d bar, what is given as 80 mm. So you convert this 80 mm into meters, so that you will have area in meters square. So yeah, it should come to me as 33.33. Are you getting this? Can anyone tell me if you are getting this?
Yes.
Okay. So now, once AS is calculated, you need KT as well. So KT is nothing but rate constant at 27 degrees Celsius. Okay. So here at 25 degree it is zero point 0.1. Into theta you are given as 1.08. Power T is 27 minus 25. So which means zero point 0.1 into 1.08 square. So calculate this. What are you getting? Answer should be 0.1166. Are you getting this?
Yeah.
Okay. So once we know all the terms, another which is left is area or the surface area of this tank. So for that, what you do? Pi by 4 d square, sorry, capital D. So this is nothing but pi by 4 43 square, right? So this should come to you as 1452.2 meter square. Are you getting this?
Yes.
Okay. So further step is to put up all the values, which is nothing but SC by SI equals to exponential minus KL AS power m is 1, A by Q power n, which is 1. Okay. I guess the formula is correct. Yeah. So SC2U is given as 20 milligram per liter and inlet is 255 milligram per liter. Then on the right hand side, exponential of minus K you are getting as 0.1166 into L you need to find out. Then AS is 33.33 into A you got as 1452.2 divided by Q. Now this Q is in meter cube per second, right? And you can see that all other units, this is also in meter, this is also in meter, this also in meter. So that all is correct, but here the time is in 1 per day. Okay, so here you need to convert this into day. So for that, what it is required is So how to convert? So time comes here. So 1 second, 1 second is nothing but it will be 1 by 3600 seconds. So 1 hour has 3600 seconds. 1 second is how much hours? So 1 by 3600. Okay. So 1 by 3600. So calculate this.
So we need to convert in per day, na?
Yeah, we are doing it in per day. Oh, sorry. This is an hour, right?
Yeah.
Yeah, thanks. So, 1 day has 24 into 3600 seconds. So there will be one more 24 here. Now tell me the answer directly for L. It should come to you in meters. So RHS is obtained as, right? T by 5, which is equals to 0.078. Now here there will be L, sorry. So to remove exponential, take logarithm to both the sides. So ln 0. So L will come out to be 5.08. So check what option it is matching. And option it is matching as 5.06. I hope you are getting this answer. Are you following this?
Yeah.
Okay, so should I move to next question?
Yeah.
Okay. So solid retention time could be defined as what should be the solid retention time? Solid retention time is what amount it is present inside the reactor per unit amount which is wasted per day. So option A matches here, right? Next question is identify the figure given below. So what type of treatment process it is? So can you tell me?
Upflow anaerobic sludge blanket reactor.
Yeah, so this is the correct answer. It is anaerobic because there is no oxygen supply here. Apart from this, upflow and anaerobic process matches here because the flow of water is in upward direction. While in trickling filter, you can say the flow of water is from top where it is sprayed from nozzle, right? So it is upflow anaerobic sludge blanket reactor. In the operations of a sequential batch reactor, the idle step occurs between decant and dash step.
Fill.
Filling.
Yes, so
Yes.
fill is the correct answer. So you can write the order as fill, then it will be react, then it will be settle, then it will be decant, then it will be idle. Next question is the relation between HRT and for the SBR systems or sequential batch reactor systems is given by dash. So which is nothing but VT into TC by 24 VF. So this derivation is given to you in the class. Okay, so how do you derive it? Um, so VT is the total volume fed divided by Q, and this Q is nothing but the volume which is of the wastewater which is fed in one cycle into number of cycles, okay, NF. Now this number of cycles can be per day, it can be taken as time taken for one cycle, okay, um, 24 by TC, okay. So in one day, what is if this much is the time taken, then number of cycles will be 24 by TC. If you put up that, so HRT will come out to be VT by 24 VF into TC, right? So option B is the correct one. Next question is higher COD to nitrogen ratio 7.5 to 30 is responsible for the formation of dash in granular activated sludge process. So here large and fluffy granules will be produced. So for granular activated sludge process to have small and fluffy. Can you check what answer we should have? Is it correct?
We are not given this question in our assignment.
Wait, I will check. I'm a bit confused right now. I will check for this question and give you the answer. Okay. If somebody knows, you can tell me. I'm not sure for this answer. I will take up this question in the next class. So, identify the plant having copper removal capacity. Out of the following, you need to find out. So, as I mentioned, this is nothing but phytoremediation, and there will be some specific plants which will be available for removal of specific type of pollutant. So, here copper is given to you, which comes under the category of heavy metal. Now, for that, all of the above can be used for remediation or removal. Okay, so all of the above is the correct answer. Moving forward, next question is wastewater flow from a small community averages 3400 meter cube per day during winter and 8000 meter cube per day during summer. So there are two seasons for which data is given. So let's first write down the data. So here Q is given to you as 3400 meter cube per day and 8000 meter cube per day, right? Then the temperature which is operated as 10 degrees Celsius because the average temperature of the coldest month is 10 degree. So you can consider 10 degree as the operating temperature. And in summer, the operating temperature, you can say average temperature of warmest month is 40 degrees Celsius. So this is the operating temperature. Now the BOD 5 is 200 milligram per liter with 70% being soluble in it. So inlet BOD is same for both. In BOD is 200 milligram per liter, 200 milligram per liter. and out of which you can say soluble BOD is nothing but um, 0.7 per 70% or zero point 0.7 times the actual BOD, which is 200. Okay. Now, K reaction coefficient K at 20 degrees Celsius is given to you as 0.25 per day, right? The temperature coefficient theta is given to you as 1.09. Find the volume of facultative lagoon to remove 90% of soluble BOD. To calculate first this, what is the amount of soluble BOD present, and you need to remove 90% of that. So you can say that whatever the amount of BOD left will be 10% of BOD soluble. To calculate this is the common term. So the remaining soluble BOD required during both the seasons, right, is 14 milligram per liter. So for this two seasons, you need to check what is the volume of lagoon required for treatment. Okay. So here uh, the formula which will be used here is nothing but final SC, which is the soluble BOD remaining by SI equals to 1 by 1 plus K into theta. Right. So it is given to you in the lecture. And here it is at temperature T. And you can substitute the value of theta as KT V by Q. So let me take a new slide. So here what you need to find out first is KT. So here for winter, K is given to you as 0.25 day inverse at 20 degrees Celsius. And the relation for conversion is nothing but KT equals to K at 20 degrees Celsius theta, or you can say psi because theta is hydraulic retention time, T minus 20. Here this factor is given to you as 1.09. So if we put up the values, 0.25, 1.09 r T minus 20. Right, so let's calculate for both the seasons. Okay, so K at 10 degrees Celsius will be 0.25, 1.09 into power 10 minus 20. So which will be 0.25, 1.09 power minus 10. Calculate this. It should come out to you as 0.105. Are you getting this?
Yeah.
Okay, so similarly for summer, the temperature is 40 degrees Celsius, right? So it should come to you as 0.25, 1.09 power 40 minus 20 point, so which will be 0.25, 1.09 power 20. This should come to you as 1.4.
1.40.
Yeah, 1.4, it's the same, right? So let's move forward. Now, if we want to find out the value of the volume, so what we have SC by SI is nothing but 1 upon 1 plus K theta. K will be different depending on the season and theta will be different. Okay. So SC by SI is given to you as 14 because this is the outlet soluble BOD divided by inlet is 140 soluble BOD divided by 1 plus K theta. So this will be zero point 0.1 equals to 1 by 1 plus K theta. And if you cross multiply this, then zero point 0.1 plus zero point 0.1 K theta equals to 1. So if you simplify further, zero point 0.1 K theta is nothing but zero point 0.9. Now on dividing zero point 0.9, like taking zero point 0.1 on the RHS, zero point 0.1 by zero point 0.9 is 9. So K theta is 9, which is nothing but K V by Q equals to 9. Now here you know the value of Q and K, and K varies depending on season, which is why volume of reactor required or lagoon required for different season will be different. If we put up the values at different temperature, then K at 10 degree will give you volume for winter. Okay, so K is 0.105 into VW by Q is 3400 meter cube per day equals to 9. So if we calculate this, you should get 291428 meter cube. So you can say that at low temperature, the rate is very low, or the rate at which microbes are able to degrade biological or the organic compound is very less. That is why more time is required for such or similar efficiency, or more volume is required if you provide same amount of time, while at 40 degrees Celsius rate is more. Okay, so if we put up the value here for summer, you should get lesser amount of volume required. Vs is 9 into 8000 by 1.4. Here the volume is again more treated, still lesser volume is required. We can say that lower the temperature, lesser will be the rate at which degradation can occur, or lesser will be the activity of the microbes. So here option D is the correct answer, which is like matching similar to our what we are getting. I hope you are getting these answers.
Somebody has given the data for that particular question in chat box.
Okay, yeah. For the COD to N ratio, which is high. So it will have large and fluffy granules because of the growth of heterotrophs. So, okay, large and fluffy granule is the correct answer. Okay. Are you getting the answer for this question for now?
Yeah.
Okay, so let's move forward. A complete mixture activated sludge process is used to treat wastewater flow having flow rate Q equals to 2 million liter per day and having BOD as 220 milligram per liter, right? Now the biomass concentration in the aeration tank is MLSS, which is in the aeration tank X 2300 milligram per liter. And the concentration of net biomass leaving is nothing but what you can say XE exit in the exit is 50 milligram per liter. Now the aeration tank has a volume of V equals to 400 meter cube. What is the hydraulic retention time and mean cell residence time of wastewater in aeration tank? So here you need to find first HRT and mean cell residence time. So HRT has very basic formula we have used many times. So please tell me what should be the formula.
V by Q.
Yeah, so HRT is very simple, V by Q. And directly we know everything. So we just need to put up the values of V and Q to find out HRT. So HRT, V has 400 meter cube. It is given. And Q is 2 MLD, which is million. Okay, so it is million liter per day. So 2 into 10 to the power 6 liters per day. Right? So if you convert this liter into meter cube, because here it is in meter cube. So 400 meter cube by 2 into 10 to the power 6. Now 1 liter is 10 to the power minus 3 meter cube per day. Okay, so it what will come out as 400 by 2 into 10 to the power 3 meter cube per day. That is also meter. So if you calculate, it should be zero point 0.2 days is the HRT.
Yeah.
Okay. Now coming to mean cell residence time. Mean cell residence time is not nothing but total amount of um, the sludge or microbes in tank divided by total amount leaving. Okay, so total amount of microbes in the tank. For that, here you are given the concentrations, right? 2300 milligram per liter and 50 milligram per liter. So in this tank, if you say of volume V, if this is the amount of uh, microbe 2300 milligram is present in 1 liter of water, you can say. Then if the aeration tank is having 400 meter cube water or wastewater, then what should be the quantity? Because you are not given, you are not supposed to use concentration, you need to use amount. So for exact amount in 400 meter cube, what will be the amount present? So for that, it will be nothing but 400 into 2300. Okay, divided by total amount which is leaving. Now leaving is in the form of continuous outlet flow which is given by Q. Okay, so continuous there is a flow rate which is coming out as Q meter cube per or million liter per day. Okay, so for Q million liter per day of flow rate, it is having 50 mg per liter of biomass present in it. So if you find out the rate at which the biomass is exiting, you can say it is nothing but 2000 meter cube per day into 50 milligram per liter of biomass is exiting from the reactor or from the process. I hope it is clear. Is it clear?
Mm, nah, no.
Okay, wait. Okay, so wait. If this is the tank, right? It has volume V, which is having wastewater plus biomass. Okay, so this is the system. This is the inlet Q in. And since it is in equilibrium, so out of the system, Q out will also be same as Q in, right? Now here there is some biomass present, which is nothing but 2300 milligram per liter. Now can you agree this 2300 milligram per liter is nothing but a concentration? Okay, so you can say how do you interpret this 2300 milligram of biomass is present in 1 liter of um, wastewater or the volume or 1 liter volume. Okay, I hope it is clear till now.
Yeah,
Okay, so if you look at the formula of mean cell residence time, what you need total amount in the reactor or in the aeration tank divided by total amount leaving the system or reactor, right? So total amount which is present in the reactor. So you can say for that in 1 liter of volume, if you have, there will be 2300 milligram of biomass present. Okay. Now
mm,
here, okay, so volume to you given for the reactor is 400 meter cube. Right. So what we are doing for total amount present in the reactor, if we have 400 meter cube volume, then what will be the quantity in milligrams of the biomass present in milligrams or any mass quantity unit. So let's say we will convert this into same unit 400 into 10 to the power 3 liter of water volume of wastewater. Are you clear so far?
yeah, yeah.
So, okay, if you calculate, you can say 400 into 10 to power 3 into 2300 milligrams. You can later convert if it is required to another units. Is the amount of biomass in the reactor.
Present in reactor.
Okay, so here it is for inside the reactor. Now, if you look what is coming out, because you can say what is the retention time, how you calculate meter cube volume per unit flow rate. Okay. So here also similarly, if you want to calculate the retention time of microbes, then what is the amount present? It is nothing but total amount in reactor. Okay, so it will be in some unit kg, okay, because it is having mass. And what is the amount of mass leaving? So it should be kg per day. So this is how you calculate the rate, okay. So for what is the amount of biomass which is leaving, what you have a flow of wastewater coming out with a flow rate of Q out, which is given to you as this 2 mld. So 2000 liter per day of, sorry, meter cube per day of water or wastewater is coming out, or treated wastewater is coming out. Now it has biomass concentration of 50 milligram per liter. Okay, so if 50 milligram of biomass is present in 1 liter of wastewater or treated wastewater, then if you have 2000 meter cube, or 2 into 10 to the power 6 liter of water, then what will be the biomass? So it is nothing but 250 into 2000 meter cube, right? Uh, Now this is per day, so this will be amount of biomass in uh, meter, this much, sorry,
leaving the system.
yeah, biomass leaving the system, which will be amount, like if it is in milligram or any weight unit, milligram or gram or kg per day, right? I hope I am
Mm.
able to clear you on this.
Yeah.
Yeah, okay. So now if we put up the values, so total amount which is coming out is nothing but 400 into 2300 divided by what is, sorry, total amount which is present in the reactor divided by coming out of the reactor is nothing but 2000 into 50, right? So if you solve this, it should be 9.2 days. So average time spent by each microbe inside the tank is nothing but 9.2 days. Are you able to understand now?
Yeah.
Okay. So that's it from my side today. If you have any other doubts so far, you can tell me, or else we can end the session.
Thank you.
Okay. Thank you so much. Okay, I will end this meeting. Thank you for joining.